Good morning or good afternoon or good evening, depending where you are, and thank you all for joining us today. So to kick things off, I thought maybe we would go through the itinerary of what we're going to discuss today. I'd like to start out by giving a brief history of wind power, follow that up with an overview of wind turbine components, how they work in different loading conditions, give an overview of geotechnical exploration and foundation options for wind turbine support, go through Geopier construction overview and design methodology, and then pull it all together at the end with a few case histories. So when I first started putting together this webinar, I found myself very curious as to how wind power has been used throughout history. Interestingly enough, mankind has been using wind power to power their sails dating back to 5000 BCE. And then being a fan of the show Vikings, I know that the Vikings and many other explorers used wind to venture from their homelands and invade and colonize new lands such as England, Iceland, and even the Americas. And eventually, the European superpowers developed powerful navies, such as the Spanish Armada, using wind power to propel their sailboats. So clearly, wind has had a major influence in shaping the world, as exploration and maritime warfare have both been powered by wind. On land, China's been using wind to power water pumps since 200 BCE, and the Persians developed windmills around 500 AD. The windmill technology was brought back to Europe by the Crusaders and became very popular in the 14th century. And by the 1800s, there were over 200,000 windmills in Europe. That technology was also brought over to the colonies in the United States, where colonists and farmers used windmills to pump water, grind grain, and cut wood. However, as with most technologies, windmills started to become relatively obsolete with the advent of the internal combustion engine and electrification programs. However, in the 1970s, there was an oil shortage that forced folks to look to alternate energy sources. California spearheaded that effort by constructing thousands of wind turbines in the 80s. Other states started to follow suit, and over the past 30 years, wind-generated electricity has grown from less than 1% to over 7% in 2020. So I found some interesting statistics that I thought I would share with everyone. Where are we today? Well, as you can see on this plot, wind-generated electricity has increased in the last 20 years from about 10,000 megawatts to north of 100,000 megawatts. To put that in perspective, 1 megawatt can power over 250 homes. 100,000 megawatts can then power 25 million homes. That's about 15% of the homes in the United States. That's pretty impressive, don't you think? Now this map shows wind capacity by state and the megawatt output per state. So you can clearly see that states like Iowa, Texas, California, Illinois, Nebraska, and Oklahoma are leading the charge, with Texas alone accounting for nearly 25% of the total megawatt generation in the United States. This map here shows what percentage of each state's electricity is generated by wind power. Over 1/3 of the electricity in Iowa, Nebraska, and Oklahoma is generated from wind power. That is truly remarkable, in my opinion. And this final map shows the cumulative spending on wind power per state. I don't think anyone would be surprised by the fact that Iowa, Nebraska, Oklahoma, and Texas are the big spenders. We've seen that on the previous slides. But they're also reaping the largest benefit. Moreover, this goes to show how much money is being spent on wind energy in the US. It's nothing to scoff at given these economic times, and we have to look to wind power in the 2020 and beyond. So I thought next it would be nice to talk about how wind turbines are composed, how they work. And I'm going to start with this diagram and work my way from the top to the bottom. So I think everyone has seen a wind turbine, and you see the main components. You've got the blades, which are connected to a rotor. That rotor is connected to a drive shaft, which turns a gear, which turns a generator. And that generator is what creates the electricity. The electricity goes down a cable and out into the grid to power our homes. What I found very interesting is at the top, there is an anemometer. This anemometer records the direction and speed of the wind, and it tells the wind turbine which way to face in order to be the most efficient. So it sends a message to this yaw drive, which is what allows the wind turbine top to actually turn and face the correct direction. This whole upper part is called the nozzle, and it sits atop the tower. And that tower goes down and rests on a foundation. Now, being a geotech engineer by trade, of course, I'm most interested in the foundations, so that's what we're going to talk about next. What you see here is two typical foundation shapes for wind turbine support. You have the octagonal shape on the left and a circular shape on the right. And for perspective, these are generally 50 to 70 feet in diameter. Now, I color-coded these for a reason. The blue portion represents the foundation base, whereas the red portion represents the pedestal upon which the tower sits. Right now, we're looking at the plan view. For a little bit more clarity, I'm going to move over to the next slide, which is a section view. Please note that this section view only represents half of the foundation, and here's the center line. So again, it's color-coded, and you can see that there's the blue portion at the bottom, which is the foundation base. You can see it's very wide at the bottom and tapers as it goes up. Sitting atop that foundation is the pedestal, which is usually about 18 to 20 feet in diameter, and on top of that pedestal sits the tower. These foundations are typically embedded about 8 to 12 feet below grade. So I thought this picture is really neat and kind of gives some perspective as to how large these foundations are. So this is clearly a circular foundation, and you can see an inspector in the back there for scale. It's just kind of hard to believe how large these are and how much steel goes into these. It's really pretty cool. So when it comes to engineering design, there are three main loads that are applied to these wind towers. Obviously, there's an axial load associated with the dead load of the structure. But in addition, you have a shear load, right? So the main purpose of these is to harness the power of wind. So you have to imagine the wind is coming at these turbine blades in order to generate electricity. Well, that wind load applies a shear to the wind turbine, and that shear induces a moment. And for simplification, that moment's equivalent to the height of the wind turbine times the shear force from the wind. So in addition to the different load applications, there are three different loading conditions that are commonly analyzed. You have the dead load or static load, which simply represents the dead load of all the components of the wind turbine. You have the normal extreme load condition, which represents the operational or service load. And what I mean by that is it's the load that's applied to the turbine under normal wind conditions in operating services. And then there's the abnormal extreme, or the transient load, which represents the loading condition under large gusts of wind. And those are temporary, they're not sustained. So slightly different from a foundation you might see for a building, under these normal extreme conditions or abnormal extreme conditions, as I stated, the shear load creates a moment. And that shear and moment results in a non-uniform applied pressure at the bottom of the foundation. So under the normal extreme conditions, what you'll typically see is a pressure close to zero on the wind side of the foundation. So imagine the wind is going from left to right on this slide. On the non-wind side, you have a much larger applied pressure due to the shear and moment that's created. Under the abnormal extreme condition, which has a higher shear load and a higher moment, you can actually have zero applied pressure for a significant portion on the wind side of the foundation, and that's a condition called gapping. What happens is you have zero pressure within this area and a much larger applied pressure on the non-wind side due to the larger moment and larger shear. So I think we have a decent handle on what wind turbines are and what the loading conditions are, right? So when you're going out and looking at a potential project, certainly you have to design for the wind conditions you're expecting. But one of the most important components is what is going to support the foundations for these wind turbines. So what I'd like to go through now is a typical geotechnical exploration program for a wind turbine project. In general, the standard of practice is to do one boring or sounding per site. Those borings can consist of standard penetration testing or cone penetration testing, CPTs or SPTs. In addition, on occasion, we'll see some shear wave velocity testing on a site, and I think that might be particularly important in a seismic zone. Now, when these borings are performed, you need to make sure that you're getting enough subsurface information to properly design the foundations. Sometimes that's to a depth of 2B, sometimes it'd be to refusal. Really what you should do is use the local standard of practice. In addition to the exploration program, these programs typically include geotechnical lab testing. That can consist of odometer testing, moisture content testing, Atterberg limits, etc. The real key is to get enough geotechnical information in order to properly design the foundations. And again, that comes back to the local standard of practice. If the local standard of practice is to use moisture contents and pocket pens, then that's what you do. However, if you have very soft soils, perhaps consolidation testing would be required. All right, so you've done your exploration, and ideally all of your sites are perfect and you can put your foundations at your planned foundation depth without any concerns. But we all know that rarely happens, particularly on a wind turbine project where you have wind turbines spread out and dispersed over acres of land. So what do you do with a site with poor soil? Well, I suppose you could do nothing, but that's probably not a great idea. What could go wrong? Well, you could have excessive total settlements, right, which could interfere with your wiring. You could have excessive differential movement resulting in tilting, which could be particularly bad. That could result in loss of efficiency or functionality. Or you could have overturning concerns, which could ultimately cause the wind turbine to tip over. More so, if you do have some minor issues and loss of efficiency, these foundations are extremely expensive to go back and retrofit. You can't simply go out and lift these back up. They're very massive, and to get down to good bearing soils after the fact would be very expensive. So what are the options? Well, option one, you could just simply move the site, right? So I have bad soils over at spot A, perhaps I'll move 200 yards over to spot B. Well, that might work out, but you might have issues with your overall planning, right? So when these wind farms are designed, they have locations that are specifically in mind based on wind pattern studies and other factors. Also, you have the issue of needing to get land rights. So for each of these wind farms are typically in farm fields, and you have to get permission from the different landowners in order to build the wind turbine. And lastly, you might go to another site and perform an exploration and find out you have the same or worse soils at this alternate site. So not only have you wasted some time and money, you still have to go back and fix one of the first site or the second site. Option two would be simply to remove the poor soil and replace it with engineered fill. That is certainly an option. We have to consider the fact that these foundations are massive. So a typical foundation is 60 feet in diameter. So if you think on a project where you have a 10-foot embedment depth for your foundation, and you have to remove up to 20 feet, you can't simply just remove a block of soil under the foundation. You also have to remove soil within the zone of influence of the foundation. So imagine a line coming down at a 1-to-1 from the edge of the foundation. Now to have a safe excavation, you have to come back at a 1-to-1. That additional removal of material for this scenario right here is 2,200 cubic yards of material. If you assume $27 per cubic yard to remove and replace the additional material, that's a cost of about $60,000. And that's only accounting for the fact that you're removing and replacing material. What if you have to dewater? What if this is sand and it's below the water table? Not only do you have material rushing in, you have to put in a dewatering system in order to be able to excavate and replace the soil. This could also impact schedule, or you could open the excavation and have it rain 2 inches. I mean, this time of year in the Midwest, you could expect a lot of rain. And then there's also the compaction requirements. So you have to come back and compacted lifts, and that can take time and money. Option 3 would be deep foundations. So deep foundations are certainly a robust solution that would help limit both total and differential settlement. You'd have a good solution, but there's a cost associated with that. So deep foundations are generally quite long. They require multiple pieces of equipment. They generally require a structural connection to the foundation. And it might be difficult to get to the proper cutoff elevation. So if you think about installing, let's say, an auger cast pile, you would grout that all the way to the ground surface. You could attempt to dip out the material or drill it out down to where you need it to be in the foundation cap. But what if you're off? What if you're too high? Well, if you're too high, then you have to chip down that concrete. And if you're too low, then you have to go in and put a cold joint to get back to where you need to be. So that can cause some difficulties during construction. And there's option 4. You could put in an intermediate Geopier foundation. So Geopier foundations would require smaller equipment. They go in very rapidly. A typical installation for a wind turbine is about 2 to 4 days. They go to a shallower depth, and they're very easy to excavate. So compared to a deep foundation, we still install these geopiers all the way up to the ground surface. However, when you go to excavate the wind turbine foundation, you can excavate right through the geopier with conventional excavation equipment. There's no need to chip anything down. You just dig right through it. So it makes it very easy to get down to your foundation depth. And lastly, you can actually design that foundation as if it was bearing on soil. All right, so when should you consider using geopiers versus the other options I discussed? So if you're considering it versus removal and replacement, geopier is generally cheaper if your undercut is about 5 to 6 feet below the bottom of footing. So for instance, in this example you see on this slide, I have a foundation that's about 10 feet below grade and an undercut requirement to 16 feet below grade. The required amount of additional material to be removed is about 1,300 cubic yards. And at $27 a cubic yard, that cost for removal and replacement is about $35,000. I would suggest that the cost to support the same foundation on rammed aggregate piers, tagging into the stiffer, denser soils, would be about the same cost, about $30,000 to $35,000. So it lends credence to the fact that the 5 to 6 foot undercut is about the break-even point between the two options. The nice thing about Geopier is if you imagine that the groundwater table is at 11 feet or 12 feet or anywhere beneath the bottom of the foundation, you don't have to worry about dewatering with the Geopier like you would if you had to undercut 6 extra feet. How about Geopiers versus deep foundations? So over the years, we've seen many jobs where we've been priced against deep foundations, and we've come up with this nice little chart that shows the price point between rammed aggregate piers being a better option versus piles being a better option. And the way this plot works is you have pile capacity on the y-axis and pile length on the x-axis. So as an example, if you had a job where to get capacity, you had 40-foot long deep foundation elements at 125 kips, you're probably better off using rammed aggregate piers. It'll be a more cost-effective solution. In particular for a wind turbine project, you'd also have the advantage of schedule, as these jobs can be installed in 2 to 4 days. You don't have to wait the 7 days for the concrete to set. As soon as we're done putting the piers in the ground, you're able to go out and excavate the foundations. As a second example, if you had 30-foot long piles at 150 kips, the piles might actually be cheaper than rammed aggregate piers. But if you're not sure, I would encourage you to price both solutions. All right, we're going to move on to Geopier Technologies, and you notice I have a detour sign in the upper right here. The reason for that is this section isn't specific to wind turbines, but I think it's important to understand how piers work, and I think it's also important as we get to the case studies towards the end. So what you see on this slide is our 4 main rammed aggregate pier systems. Going from left to right, you have the GP3 system, which is our standard drill and fill system. In the middle, we have the impact and rampack systems. Those are our two primary displacement systems. And on the far right, you have our X1 system, which is our sort of our hybrid. It's maybe 80% GP3 and 20% impact. So we're going to go into a few of those in more detail. We're going to start off with the GP3. So GP3 is our bread and butter. It was the basis for the original Geopier, and it's what we use on the majority of the projects we work on. So what are the key components here? So it's a very nimble system. It requires 3 pieces of equipment and 4 personnel. So see on the left here, you have a excavator mounted auger, which augers out the holes. You have a skid steer, which delivers the aggregate to the hole locations. And you have a excavator mounted tamper, which creates the pier in the ground. And these go in the ground very quickly, and they're very safe and clean. So quick note on how they're constructed. It's really a simple process, to be honest. You start out and you go to your pier location, which is flagged in the field, and you excavate down to your design depth. And that design depth is determined by Geopier. You pour in some open graded stone and you tamp that stone in place. And what we're doing in that process is we're creating a stable base at the bottom of the cavity from which to create our pier. From that point forward, we add aggregate to the hole, put the tamper in, create a 2-foot lift, put in another 3 to 4 feet of aggregate, put the tamper in the ground, create a 2-foot lift, so on and so forth until we get to the ground surface. So each of these bulbs here represents a 2-foot lift of compacted aggregate. What I'm going to show you now is a video that walks through that process. So start out with step 1. Step 1 is to auger down to your design depth. You're going to add your base stone, and you're going to compact that in place using the tamper to create a solid base from which to build your pier. You're going to place several feet of aggregate, and you're going to compact that down with the tamper to create a 2-foot lift of compacted aggregate. And you're going to repeat that process in 2-foot lifts until you get up to the ground surface. Okay, the next system I'd like to discuss is the Geopier impact system. This is one of our primary displacement systems, and it's an important thing to note that there's, every now and then we hear the myth that you can't install geopiers below the groundwater table. Well, you certainly can, and this is how you do it. So what we see here with the impact pier is a mast rig with a mandrel, a hopper on top, and a hammer. And this is a bottom feed system. So what we do is we use the telehandler that you see here to put rock into the hopper. And then we advance that mandrel down to our design depth. Now you're probably thinking to yourself, well, how do you advance the mandrel without getting soil inside the mandrel? And we have this nifty configuration. So what you see in the bottom left of this slide is what you would see if you were to look directly up into the mandrel. And I know it doesn't seem like much, it's just a bunch of chains hanging down like tentacles. However, when we push down the mandrel into the soil, these chains bunch up and perform a plug. And that plug prevents soil from getting into the mandrel. And it has a second purpose, which I'll describe in a minute. So you advance the mandrel to the design depth, and then you withdraw the mandrel several feet, 4 feet. When you withdraw that mandrel, those chains go lax, and they look like they look in this picture. That allows the aggregate to flow through the mandrel and into the hole, so we have material from which to build the aggregate pier from. We then advance the mandrel back down 2 feet, and as we advance that mandrel back down, these chains re-bunch up and re-engage and create a compaction surface from which we can build our piers. And much like the GP3, that process is repeated over and over until we get to the ground surface. The main difference being this is a bottom feed system where the aggregate flows out the bottom of the mandrel, whereas opposed to the GP3 where we're dumping an aggregate from the top, i.e. a top feed system. So what are some advantages of the impact? Like I said, it's a displacement approach, which allows us to install piers in caving soils below the water table. It has an added advantage of being able to install piers to 45 feet. So I didn't say this for GP3. However, GP3 has a limitation of about 25 feet plus or minus. These piers can actually go 45 feet. And they're great for contaminated sites. Probably not a huge issue for wind turbine projects. However, if you're working in an urban environment with environmentally impacted soils, you can use a displacement system and you're not actually creating any spoils. So there's no reason to haul off material to an expensive landfill. And much like GP3, they're installed very rapidly. You can put in 40 to 100 piers per day. All right, we have an installation video for impact as well. So the mandrel is advanced to the design depth. Remember, the chains inside are creating a plug. And as you withdraw the mandrel, the chains go lax, the aggregate comes out, push back down, the chains bunch up, form a compaction surface, and create these 2-foot lifts of aggregate. You repeat that process up to the ground surface. All right, I'd like to discuss one last rammed aggregate pier system, and this is the X1. Notice that we are not going to talk about Rampact. It is very similar to Impact. So the Geopier X1 is our newest of the rammed aggregate pier systems, and like I said, it's kind of it's a bit more nimble than GP3. It has a little bit of an impact flavor to it at times. So it generally works best in the same soils as GP3, some clays, holes that'll stay open. Pre-drilling is generally required unless you have a clean sand. It can go to depths of 45 feet. And then the cool thing is there's no reason to trip out of the hole. So if you look at the mandrel, it's a little bit different than both the Impact and the GP3. So at the base, you have a compaction chamber that is similar to Impact piers. Inside of this cylinder, you have the same chains that allow for bunching up to create a compaction surface and going lax to allow aggregate to flow through. But this compaction chamber is attached to an H-beam. And the nice thing about the H-beam is once you drop the mandrel into the hole, there's no reason to trip back out of the hole like you would with the GP3. You can simply pour in the aggregate from the top and it'll flow through the webbing down to the compaction chamber. This allows for much more rapid installation. One added bonus is it works in a mixed profile. So on occasion, we run into sites where we have, let's say, 10 feet of soft clay underlain by 5 feet of loose sand. That's below the water table. And we go, oh no, we might have a caving issue. We could switch to impact, but there's maybe some less efficiencies there. So what we can actually do is we can charge the hole with aggregate, i.e. pour in more aggregate than we need, and that'll create a temporary casing that prevents the sand from caving into the hole. So we actually use the compaction chamber and the aggregate to provide a casing of sorts so that we could advance down through the sand without having to use real casing, which adds pieces of equipment and time to the project. So we have an X1 installation video as well. There's a live action video as well as an animation. The live action one is really neat. So this is a project, I believe, that's in the Dakotas. And you can see the 3 pieces of equipment that are used. On the right, you have the excavator mounted auger prepping the holes. On the left, you have the X1 mast rig with a mandrel. And in the middle, you have the skid steer delivering the material. And here's the live action video. Auger out to your design depth. Place your first lift of material. Advance the X1 mandrel down to your design depth and create that bottom base from which to build the rest of your pier. And now instead of coming out of the hole, you just stay down in the hole, add aggregate as you go, and go up 4 feet, down 2 feet, go up 4, chains go lax, lets aggregate through, push back down, chains bind up, create a compaction surface, so on and so forth, in 2-foot lifts till you get to the ground surface. All right, so we've gone through the rammed aggregate piers. I'd like to spend a little bit of time talking about our our arsenal of rigid inclusions as well. So, you know, there are sites out there where rammed aggregate piers simply aren't ideal. You have sites with deep soft clays, you might have sites with organics, you might have sites where you simply want higher capacity elements and higher bearing capacities. So we have several systems that we use to accommodate those problems. Going from left to right, you have the grouted impact piers. So these are basically the same as our impact piers with the addition of grout, as the name would apply. So what we do is we construct the impact piers the same way, with the one exception that we actually add grout through the top in the hopper via a hose, and that grout mixes in the mandrel as we create the pier to create a cementitious pier element. Next, we have Geopier GP3 with CTA. So CTA stands for cement treated aggregate, and it's simple as the name implies. It's aggregate that has cement mixed in with it. So we would construct a Geopier GP3 as we would using normal aggregate. However, the cement mixed in with the aggregate hydrates over time in the ground to create a cemented element. At the far right, we have geoconcrete columns, or GCCs. This is one of our relatively newer technologies, and it consists of a bulb of concrete at the bottom and a extruded column of concrete up to the ground surface. These are generally very high capacity elements that we would use for high-rise structures or structures with very heavy loads. And you'll notice that I did skip over ArmorPact, and that's because I'm going to talk about ArmorPact in more detail in the upcoming slides. Okay, so what is ArmorPact? So ArmorPact is basically a HDPE shell that comes in either a 9.5 or 14.5 foot section. And it's ideal for soil profiles where you have organics or soft clays or very loose sands that simply aren't going to be able to support the loads that you need. So if you look at the profile included on this slide, what's represented in here in the green is an organic soil layer. And what happens is we advance the shells so that they tip into a competent bearing soil, and they completely encapsulate the pier through this organic or soft zone. And what the shell does is it provides confinement to the pier. So we do compact aggregate within the shell. However, the shell itself provides confinement, so there's no long-term loss of strength into this softer material. You don't have to worry about the pier bulging into these soils, which could cause excessive settlement of whatever you're trying to support. And on top of that, you have a ram-packed stem, which is one of our displacement systems. One of the other beauties of ArmorPact is the shell is extremely stiff. It has a modulus of about 4,000 KSF, so it provides excellent settlement control in these soft soils. So what sort of equipment do we use for ArmorPact? Well, in general, it's pretty much the same as what we use for impact or rampact. The main two differences are you have a custom mandrel that we use. It's similar to a rampact mandrel, but it's outfitted specifically so that it works well with the shells. You can see that the shells are slightly tapered. The mandrel is tapered as well so that it doesn't stick inside the shell. And then also you have a specialized skid steer that has this grabbing arm for picking up the shell and putting it where you need it to go. How are these installed? It's a pretty simple process, right? So you put your shell right over the flag where you want your pier to go. You advance the mandrel into the shell, and you advance the mandrel and shell together to the design depth. You're going to construct a ram-packed pier inside the ArmorPact shell itself in 2 to 3 foot lifts. And once you're above the top of the shell, you create a ram-packed stem, if you will, which is just a displacement pier on top, and 2 foot lifts up to the ground surface. So we have one last video for the day. This is the ArmorPact system. Now there's one thing I want to point out that's very important during this video. So you can see they're advancing the mandrel to the design depth, and they place that first 3 foot lift and they compact it down. Now you see that shell moved when they compacted that first lift. That's okay. That means we're engaging the bearing soils and we're getting the capacity we need. The one thing I would want to caution is if you were to push that shell too far down, or if this organic was higher, you could actually have the top of your shell drop below the organics. That would not be an ideal situation, as you would have a portion of your pier that is not confined within that organic zone. So it's important to have good quality control during armor pack construction to make sure that does not happen. So I do apologize. Unfortunately, we didn't have enough time to go through grouted impact piers and geoconcrete columns. However, I am excited to say that we have another webinar series coming up in a couple weeks that is specific to rigid inclusions, and will go into the design and construction and installation in significantly more details. So please keep your eyes peeled for that invitation. All right, so this is a bit of an abrupt transition, but we've gone through all of the Geopier construction and installation processes. We're going to come back now to the wind turbine design. So you've got a Geopier project and or wind turbine project, and Geopier is the right solution. How do we design these things? So there are basically 6 things that we look at primarily when it comes to design. Number 1 is pier layout. Number 2 is we look at the total settlement. Number 3, and probably most important, is we look at differential settlement. Part of which is a function of the rotational stiffness, which we're going to go to in pretty good detail. And then we also look at bearing capacity and overturning. So starting with pier layout, you probably remember these figures back from when I was talking about the loading conditions, right? So you have the normal extreme condition, which represents normal operating conditions. And then you have the abnormal extreme conditions, which is a transient condition, let's say a heavy gust of wind, right? But the important thing to note is that the load is not uniform, as we stated. So if you were to think about how to support one of these turbines, you're going to want to put more piers where the heavier loads are going to be. So intuitively, you're going to need more piers around the perimeter of the footing than you would in the center. So that's exactly what we do. So here's a typical layout for a project. You can see here we don't really have many piers in the center, but as we get farther out to the perimeter of the footing, the pier density gets larger, because that's where we need the piers to do the most work, right? The pier spacing itself is based on our overall design, and it's based on a per pier capacity. We don't want to exceed the capacity of the piers. And we do allow for a 33% increase, though, for transient conditions. All right. So the next thing we would look at would be settlement control. When we look at settlement, we break out our settlement into a 2-phase approach. We have our upper zone soils, which would represent the pier reinforced soils, which starts at the base of the pier and goes up to the bottom of the foundation. And then we have the lower zone soils, which is everything underneath. We typically analyze settlement to a depth of 2B, which would be twice the foundation width, which is a normal standard practice, or we'll stop our analysis once we hit a refusal type material. And it should be worth noting that we use the dead load only when we calculate the settlement. So the settlement is calculated using what I was taught was called the Flea formula, and that is simply deflection equals the force times the length divided by the modulus times the area. So everyone who took a mechanics course probably recognizes that formula. So in the case of settlement of the upper zone, the force times the area in this equation is the same as the applied pressure times some sort of influence factor, right? So for foundation design, you would consider some sort of Boussinesq stress distribution or Westergaard. And for a large foundation, such as a wind turbine foundation, we would expect that these influence factors would be quite large, i.e. you don't get a lot of reduction of the applied bearing pressure with depth, at least within the pier zone. The H represents the height of the layer, or the length of the element, and E is simply the composite modulus of the soil in the piers, which I'll talk about in a second. One of the beauties of this approach is you can use multiple layers. If your soil is uniform throughout, then great, you can use one layer. But if you have, 30-foot long piers and every 5 feet your soils change, you can use 6 different layers if you want to. So the big key here is coming up with the right value for your E. And what we do is we come up with a composite modulus that is weighted based on area. And what I mean by that is if you were to look down from space at a plan view or an excavation for a foundation, and you could see the pier elements and you could see the soil in between, and you say, oh, there's about 10% of that area is composed of the pier elements and 90% is the soil. We just take a weighted average. So as a quick example, if you had a pier modulus of 3000 KSF and 20% of that footprint is piers, and your soil had a modulus of 200 KSF and it would compose of 80% of that footprint, your composite modulus for that material would be 3000 KSF times 20% plus 200 KSF times 80%, giving you a value of about 760 KSF. For the lower zone, what we'd simply do is we would use normal geotech analysis procedures. We would use some sort of elastic modulus value for granular soils, so your clean sands, your silty sands, your clay sands. So let's say you did an SPT on a project and you had silty sands at depth, you could maybe use 20 to 25 times the N value to come up with a E value in KSF. If you have clay soils at depth, you would use consolidation theory. And the real key here is to not only properly identify a recompression ratio and a compression ratio, but to make sure you're not going into virgin compression, right? So usually that ratio of recompression versus compression is somewhere in the 4 to 10 range. So if you're wrong, your settlement could be 4 to 10 times higher than you thought it would. So it's very important to make sure you understand the stress history of the soils. And you could use local standard of practice. You could use laboratory testing, odometer testing. You could relate it to Atterberg limits and moisture contents, whatever is the standard of practice within your local jurisdiction. Right, so a little bit more important than total settlement is rotation or differential settlement of the turbine. Again, the turbines don't really like to tilt. They can lose efficiency, lose functionality, or potentially tip over. A normal tolerance for wind turbine is about 0.172 degrees or 0.036 inches per foot. Well, what does that mean exactly, right? So if you look at the figure in the bottom left of the slide, you can see this phi angle represents the rotation of the foundation in radians or degrees. That's the 0.172 degrees that it can occur as far as rotation goes. If you were to look at it in terms of 0.036 inches per foot, that means for every 1 foot of diameter of foundation, this side of the foundation, the right side, can settle 0.036 inches. So as a for instance, if you had a 60-foot long foundation, it can move 0.036 inches per foot. You can have a differential of 2.6 inches across that foundation. That's not really that much for across 60 feet. So it's pretty important that we make sure we understand what that rotation is going to be. And we look at that one of two ways. We look at it two ways. We look at it from a static loading condition using the elastic modulus, and we also look at it from a dynamic loading condition using the shear modulus. So for the differential settlement method, what we would simply do is you would calculate the settlement on the wind side or the left side. You would calculate the settlement on the right side or the non-wind side. You'd subtract one from the other to figure out the differential settlement across the foundation, and then you would divide that by the actual foundation width. So as a for instance, if you had settlement on the non-wind side of 2.4 inches and settlement on the wind side of 0.6 inches, your differential across it is 1.8 inches, and the rotation would be 1.8 inches divided by 60 feet, which is 0.3 inches per foot, which is less than the 0.036 inches per foot criteria that we just saw. So the evaluation using the dynamic approach is a little bit more involved. I'm going to try to walk through it in some detail here. So what designers will look for is a minimum rotational stiffness, and that's usually in the range of 15 to 200 giganewtons per meter per radian, or 11 million to 148 million kip feet per radian. Rotational stiffness is calculated using the foundation radius, the shear modulus, and the Poisson's ratio. The shear modulus of the soil and the Poisson's ratio of the soil. And it's shown in this expression right here. And if you were to run the analysis and figured out that your rotational stiffness of the in situ soils is inadequate, you could always install round aggregate piers to increase the shear modulus G. I'm going to talk about how we would do that. So similar to what we did for the elastic modulus approach for settlement, we take a composite modulus for the shear modulus as well, right? So it's a weighted average based on the area of the pier versus the area of the matrix soils between the piers. So what we need to figure out is what is the shear modulus of the geopier and the shear modulus of the soil. Well, we've run tests at Iowa State and have determined that the shear modulus of the pier elements is about 6,000 KSF. For the matrix soils between the piers, there's a couple steps that are involved. So we have to start with the static modulus, which is the modulus that you would use if you were going to calculate settlement of a foundation. And you're going to use the chart shown here in the bottom right to come up with the maximum modulus, which is the modulus that you would have at very low strains. So most of the soils that we would have under a wind turbine foundation, at least if it was going to be reinforced with Geopier, has a static modulus of about 4 to 7 megapascals. Starting from that point, we come up and we intersect the lowest curve, which would be the most conservative approach, and this was a curve developed by Alpen. And we come across and we find what the ratio is between Emax and Estat. It turns out it's about 10. So long story short, Emax, or the modulus at small strains, is about 10 times E static. You could then come up with a Gmax using this expression here, where Gmax equals Emax divided by 2 times 1 plus the Poisson's ratio of the soil. But we're not quite there yet. There's one more step. So the Gmax for the soil and the Geopier is for small strains only. And wind turbines don't have small strains, they have larger strains. So we need to degrade those shear modulus values for a wind turbine application. And that cyclic shear strain for a wind turbine is about 0.1. So we've got one more nifty chart that we use, wherein this measures, so we got cyclic shear strain on the x-axis and the ratio, degradation factor, if you will, along the y-axis. And here you see a bunch of curves, and these curves are for different soil types and clays with different PIs. And I think it'd be best just to run through an example. All right, so as a quick example, if you have a maximum shear modules for a Geopier of 6,000 KSF, maximum shear modules for the soil of 600 KSF, a area placement ratio of 0.1, Poisson's ratio of 0.4, and a radius of 30 feet. You would first come up with your degradation factor for the pier. Piers are essentially crushed gravel. So I'm going to start here at the cyclic shear strain of 10 to the minus 1. I'm going to come up to, let's say it's not quite the gravel curve, but maybe the sand gravel area. Come across, and I'm going to have a degradation factor of 0.3. So it's a 70% reduction for the Geopier element. Same exercise for a clay with a PI of 15. Come up to the PI 15, come across, degradation factor of 0.4, so a 60% reduction. So your large strain shear modulus for the pier is 1800 KSF. Your large strain shear modulus for the soil is 240 KSF. Come up with a G comp based on the area. So 10% is Geopier, 90% is soil. You get a composite modulus of 396 KSF. Calculate your rotational stiffness using the equation we saw before that relates the rotational stiffness to the shear modulus, the radius, and the Poisson's ratio. And you end up with a value of about 48 million kip feet per radian, which falls within the range of what the typical ranges would be for a project. You just have to make sure it meets the designer's criteria. If it does not, you could always add more piers to increase that shear modulus. All right, the last two things we analyze are bearing capacity and overturning. So in general, bearing capacity does not control our design. We have a very large failure surface for wind turbines. The pier zone itself has a very high shear strength, so the friction angle of a pier is somewhere in the 45-degree range, so you get great resistance through the piers. And in general, the applied pressures aren't all that large. So we are generally able to meet or significantly exceed the factor of safety of 3 for wind turbine applications. However, if you are interested in learning more about bearing capacity and how Geopier designs for bearing capacity, we have a technical bulletin on our website. If you go to our website and look up documents, there's a technical bulletin 2, bearing capacity of Geopier supported foundation systems for your reference, and it walks through how we analyze bearing capacity for all foundation applications. All right, lastly, we analyze overturning. So overturning is simply evaluating the sum of the resisting moments versus the sum of the driving moments. So the resisting moments for a wind turbine is the dead weight of the superstructure, the foundation, and the soils on top of the foundation. And the driving moments are induced from the wind shear that we talked about much earlier. So the wind shear creates a moment. You would sum the weights of the superstructure, foundation, and soils about the toe of the foundation, divide that by the driving moments, and come up with your factor of safety. And in general, a factor of safety of 1.5 or better is acceptable for wind turbine applications. All right, so what I'd like to do now is I'd like to kind of hopefully bring everything together by going through 2 quick case histories with you. So the first is the Jordan Creek Wind Project in Indiana. Our scope of work on the project is 11 wind turbines. These are very standard size, 62.5 feet in diameter, axial loads in the 625 kip range, shear loads in the 125 to 150 kip range, and moments in the 37,000 to 45,000 kip foot range. Normal design criteria, 3 inches of total settlement and 0.036 inches per foot of rotation. So we're going to jump over to the soil profile on the right. These were CPT borings. You have a couple feet of soft clay, 7 or so feet of medium dense to dense sand, then all of a sudden you have some problem soils. You have some medium stiff clays that degrade to almost soft clays, and then that stiffness picks back up to a medium stiff, to a stiff to very stiff material, and then a dense sand. Other thing worth noting is this sand is actually below the groundwater table, which will impact not only some of the options we look at, but even our own design. So what are the solutions? Well, you could potentially move the site. You could find a site with better soils, but we talked about how that would require additional exploration. It might not work with the overall planning. It could affect schedule, et cetera. It might not be a better option. You could do over excavation and replacement on this project. So you could remove all the soils down to about 24 feet. However, you're going to be below the groundwater table with sand, and it's going to require an additional 3,400 cubic yards to be removed. And a last option would be deep foundations down to, I would assume you'd have to go down to about 40 to 45 feet. And then lastly, there's obviously ground improvement. And since this is a case history, clearly that is what they selected. So our solution on this project was to install impact piers. And we elected to put in impact piers because if you recall, those are displacement piers with a bottom feed system. And we were able to drive the mandrel through those caving sands without any issue down to our design depth and construct the pier without having any caving or contamination of the pier itself. We ended up using a pier layout of about 68 piers. It could install the piers in 2 to 3 days apiece. Well, why did they use Geopier? What was our value proposition? So these sites cost about $30,000 to $40,000 per site to install the piers. Removal and replacement would have been another 3,400 cubic yards at $27 a yard. That would have cost $92,000. So we had a benefit of about 2.5 to 3 on that. And then going back to the chart, this is a kind of a reverse way to look at it because I don't know what the pricing was on deep foundations, but assuming that the foundations had to go down to about 40 to 45 feet, they would have had to have had a capacity of 150 kips a piece, 160 kips a piece, in order to be more efficient than rammed aggregate piers. I did a quick calculation this morning. I'm not saying it's 100% correct, but I came up with a capacity of about 120 kips, which would put the price point well into the wraps being more cost-effective portion of the plot. Okay, a second case history. This was a much larger project. This was 30 wind turbines in Macon County, Illinois, the Twin Forks Wind Farm. Similar loads as the first case history, 60-foot diameter foundations, 125 to 140 kip shear loads, 600 kip axial loads, and moments in the range of 39,000 to 46,000 kip feet. Same design criteria, 3 inches of total settlement and 0.036 inches per foot of rotation. So this soil profile is a little bit hairier than the case history number 1. You start out okay, same couple feet of soft clay and some denser sands, very similar to what we saw in case history 1. However, beneath that, you start to get into these sensitive, fine-grained materials, which if you're looking at a CPT log, generally means organics. We cross-referenced that against some of the SPT boring logs at neighboring sites, and it turns out, yes, there was organic material on this project. Moisture contents were in the 80 to 100% range, and LOIs were in the 15 to 20% range. Generally, we start to get a little concerned when moisture contents are above about 50% and LOIs are about 10%. So what were the options? Again, you could have moved the site. I'm not going to get into that again, but same risks. And in fact, a lot of these, since we did 30 turbines, there were actually a lot of sites that had organics. You could over excavate and replace. In this case, you would have to go 26 feet, which results in an additional 40,000 cubic yards of material. I'm sorry, 4,000. Or you could put in deep foundations, which I anticipate would go down to about maybe 36 to 38 feet or so. So once again, since this is a case history, this was clearly a Geopier job. We went with the armor pack solution on this. This is the rigid inclusion system I talked about earlier. The importance on this is that we were a little concerned about the organic zone from about 15 to 20 feet. We could have put in a rammed aggregate pier. However, over time, that pier could have lost confinement and we could have had unfavorable total and differential settlements. So we went with the armor pack pier, which provided confinement through that organic zone and within the softer clay zones. We advanced the mandrel down until we got a refusal down on this material at about 26 feet, installed the shell, constructed the pier inside the shell, and then put a ram pack stem on top. Ended up with about 64 piers per site, and it took about 2 to 4 days per site to install the piers. What was the value on this project? So our piers cost about $45,000 to $60,000 per site. Removal and replacement would have cost about $109,000, so about double our cost. And the piles were a little bit more comparable if I did my calculations right. So they would have had to been about 145 kips plus or minus to be with that same price point as piers. I estimated about 120, so it still falls beneath the curve here where wraps are more cost effective. All right, so you're all asking yourself, why Geopier? Well, I think I've gone through our systems pretty well to know that we have enough technologies for almost any challenge. We can handle sands below the water table, we can handle clay sites, we can handle organic sites. I didn't even touch rigid inclusions, but those have capabilities that go well beyond what I discussed even today. We have proven performance. We've worked on dozens of projects throughout the US and really across the world. We have local offices and regional engineers throughout the US to help look at projects. And it's, these are projects that we take from the start and we don't step away from until that last pier's been in the ground and everyone's satisfied. So we'll help you vet your projects from the start. We'll give you our advice and our pricing. If we win the project, obviously we'll be on site during installation to make sure nothing goes wrong. and we'll follow it through to the end until the foundation's poured and everyone's happy with the performance. And I think one of the keys, especially for wind turbines, is we can put these things in 2 to 4 days. And as soon as we're off site, you can start excavating. There's no additional delay required. So we come in, put in the piers, leave, and you can have your foundation ready to go within the next couple days. Just a quick snapshot of our experience. You've got many projects throughout Iowa, Illinois, and Wisconsin, which is no surprise based on some of the charts and figures I showed in the first few slides. We've done work throughout the rest of the US. We've also done some international work. We done work in Costa Rica, Chile, Mexico, and several projects in Germany as well. And well over 1,000 megawatts supported. I imagine that number is much higher now. So again, if you find yourself working on a wind turbine project or know somebody who is and needs some advice on how to tackle some poor soils, don't hesitate to reach out to Geopier. This map shows where all of our local regional engineers and offices are, and we're ready to help you out. You can either email the websites you see on the bottom of this slide, or you can go to our website and go out and fill out a project feasibility form, and we'll have the right person reach out and call you as soon as they can. So that's the conclusion of the webinar. I hope everyone enjoyed listening to it as much as I enjoyed delivering it. And with that, I bid you adieu. Thank you.